All right. Good morning, guys. So today would be the last topic of this course. So next Tuesday would be the exam on no, not Lumen. Blackboard. So I will make it available from 9 to 11 next Tuesday, and you have the time to complete the test. All right. So the format would be all either multiple choice or short answers. You don't have to write many things on the exam. You can anyway because it's on Blackboard. Um, Next Friday, however, we will have a makeup session from 11 to 1. So not the usual class meeting time, so it's 11 to 1. Okay, they would be that May 7, May 15. 7 to 1. And if I remember correctly, the final would be on next Monday. So which is be 15, 16, 17, 18. So 18. That would be the class meeting time 9 to 11 a.m. in the morning. Again, the final will be the same as the exam 3 will be online on Blackboard. Just submit everything there. Right? Nothing um it's a bit strange because you have a distance learning for the whole semester, so the format of the exam is completely changed. um uh, we will do the best. Sorry, any questions?
So for the final is
Mhm.
basically everything that homework that you gave us, because I know you skipped a couple of chapters.
Yeah, so the thing is, I skip a little some chapters in chapter 3, some chapters in chapter 4, and we only get up to chapter 6.2. So I would post the review sheets during the weekend, hopefully, so that you will have a grasp on what we have been going over for the whole semester. And the purpose for the makeup class on Friday is that we will have a general review of the whole class. And if time permits, we can go over the exams, we can go over the take-home projects if you guys want. So basically, the makeup class is the whole review, and that's the only time that we can, have time to go over the whole semester.
Okay, thank you.
Mm-hmm. Right. So let's begin today's class. All right. So today's class focus on um, maps from uh, uh one coordinates, let's say, to another coordinate. All right. So basically, maps from one um, Euclidean space to another Euclidean space. Right. So before we get that, and let's get some definitions, right? What is one-to-one and what is on-to, right? So a one-to-one function means that for any point in Rn, or any 2 points in Rn, if their image is the same, that means that they must be at the same point. So see here and here, right? You have a mapping from, let's say, some subset in Rn and subset in Rm. 1 second. So the homework, I haven't made the submission online yet. I will make that over the weekend. So basically, you have until the end of semester to finish your homework 3. Let's make it the day on the final. All right. So let's submit everything before the final, so that I have some time to grade them. And yeah, we don't. No, there's no Zoom. So just do the exam on Blackboard. Right. Any questions?
Is it gonna be on course material or like available tools? I forgot on Blackboard for the test on Tuesday.
So for the test, it will be under the course materials. It will be a test assessment, and when you you can only access them, meaning you will only be able to see them during the time on Tuesday. So that means from 9 to 11, it will only be available there. And make sure you submit everything before 11, before it's gone. Otherwise, your work won't be saved. Okay.
Okay, and for the final, is it gonna be the same format, or do we have to take a picture and upload it?
It's the same format. So do everything on Blackboard. You don't need to submit anything, right?
Okay, thank you.
Just do the Blackboard thing. All right. So I know it's an online test, and that means you can just reference any notes if you want. Right? Any formula sheets is fine. And for the time, you don't. So I would make it suitable for you to finish in time. That means you should be able to finish in 2 hours. If you struggle, that means you need to go over the material more, right? So let's get back. So let's say you have a function, right? Transform points in Rn to Rm, right? So a one-to-one means that such scenario won't happen. You have 2 different points mapping to the same point. That is not going to happen, right? What will happen and what has to happen is that 2 different points maps to 2 different points in the range. Right? So if you have the same point in the domain, range, their origin, right? When you trace back in the domain, it has to be the same point. So that is what it means for one-to-one. On-to, however, on the other hand, means that every point in the range here get maps to. So that means for any point in here, you can find some point in the domain such that it maps to this point in the range. And that goes to every point in the range. So that means this scenario won't happen, right? So when you have the image of the whole domain, it must be the set of the range, and you can have some outer rim such that it doesn't have any point that maps to. So that is what, so that doesn't happen. This is what is going to happen. Okay. So that is what it means for one-to-one and on-to. Right. And I think I have some typo here, and this should be M. Nothing major. So if you have a map that is both one-to-one and on-to, that means there is a term called bijection. So bijection means it's both one-to-one and on-to. So on the side note, one-to-one also means injective. It's just another fancy name for one-to-one function. Onto is, there is another name as well, it's called surjective. And as long as you have mappings, and injective and surjective will have a significance, right? Especially when you go to 260, linear algebra, you basically hear these two words every single day. All right, because linear algebra focus on linear maps, and there are some properties for injective maps, and there's properties for surjective map as well, right? So in this case, we will focus on the maps, right, that are bijective from Rn to Rn, right, same dimension. So basically, you can think of a transformation from an area or region in Rn to another region in Rn. So this is a transformation. Right? So for example, if you smash a ball into a and a rectangular box, for example, that would be a one kind of transformation that is bijective, right? Or you have, in R2, you change from, let's say, a circle, but in this case you have Cartesian coordinates, right, to a disk in now you have polar coordinates, right? That would be another type of bijective map, right? In this case, you just represents point in Cartesian coordinates, right? XY, meaning the x squared plus y squared equals to 1 becomes polar coordinates, right, are in this case is r sine theta and r cosine theta. So yeah, this is a type of we call this change of variable. And when we have integrations in one set of variables, and you wanted to change the integration on the other set of variables, right? there is something you need to do in order to make the integration works, right? Because, for example, let's say you have integration, double integral, let's say, on the circle, actually the unit disk, meaning x squared plus y squared is only equal to 1. This represents the area of this circle, and this should be equal to what? Pi r squared. We all know that. But if we change it to polar coordinates, right? This means you integrate it when the radius is from 0 to 1. So this is dr. And the theta, the angle is from 0 to 2 pi. D theta. Right? This is the iterated integration in the polar coordinates. And you can see that when you do this, you would get 2 pi. And this is not the same thing, right? And you should, we should be able to get the same thing because we just changed the variable, all right? The points here are the same, right? Because when you change from Cartesian coordinates to polar coordinates, it's 1 to 1. Right? You won't get two different variable for the same point. Right? You didn't change. You wouldn't transform one point to two different points in the polar coordinates, nor two different. One point in the same point in the polar coordinates has 2 points in the Cartesian coordinates to be mapped to. Right. This is a one-to-one and both one-to-one and onto mapping from Cartesian to polar coordinate, and yet two integrals are not the same. Right? So what is missing here is the Jacobian determinant. This is the one thing that is missing when you change from integration in one set of variable to integration in the other set of variable. All right. So the Jacobian determinant is basically the determinant on the partial, on the matrix of the partial. Right. This is the matrix, matrix of partials we have been familiar with in chapter 2. 1 second. Oh yeah, go ahead.
The argument for this in Calc 1 is usually stated, because they don't mention the Jacobian, that d theta is not a unit of length, and in order to get a length, yes, a unit of area, you need a length times a length.
Exactly. All right. So remember in R1, all right, when you do the Riemann sum, of course, right, the integration is the area under the curve. Right? So when you change from this set of variable to another set of variable, the base length change, right? Because now suppose it's delta x. Now it's delta u, because you change the variable from x to u. So the length of the base changes from delta x to delta u, while you just keep the top unchanged, right? Because f of x just change to f of x of u. But since the base changed, the area changes, right? Because now xi times delta x becomes f of x ui times delta u, and there is a delta x over delta u. Okay, so when you have the Riemann sum, when the when the limits go to infinity, this becomes what? Dx du.
That the Jacobian in one variable?
So that you can understand it as the Jacobian for one variable, but when, of course, when you move to multi-variable cases, right? Now, for the Riemann sum, we are not just multiplying one side of the rectangle, right? Because for a for example, R2 to R2, you have delta x times delta y, this rectangular box, to delta u, delta v. Right? So now, in order to account for this change of area, the thing you should be multiplying would be the determinant of the Jacobian, right? Because you have delta x divided by delta u, delta x divided by delta v, and delta y divided by delta u, and delta y divided by delta z. Oh, sorry, delta v, right? And when the limits as n goes to infinity, this will be equal to the partials. That is the definition for partials. And that is the definition for the Jacobian determinant. So geometrically means in R2, or for example, the Jacobian determinant accounts for the change of area, changing area from the delta x, delta y to another set of variable, delta u, delta v. And of course, when you have the Riemann sum, the area would be not just times delta u, delta v, but another factor of Jacobian determinants in order for these two to be the same. Right? So when you have the Riemann sum, right, you don't not only do you have f du dv, but another factor of Jacobian determinants. All right.
Do you need a different Jacobian to go back the other way, or can you use the same Jacobian?
What do you mean?
If you wanted to go from u to v, from uv to xy, would you use this? Could you use the same Jacobian if you wanted to?
From uv to uv to xy, now the partial becomes partial u, partial x. So everything is flipped. You see that?
It's going to be completely different then.
Yeah, it will be completely different. Yes.
Okay.
Yeah.
Thank you.
So we were okay. So formally is stated as the theorem here, right, for R2 to R2. So for example, if the elementary region, right, you have elementary region D, right, and the transformation function T would be just transforming the points in D, right, to another point in D, right. So in this case, D and D star, right, are the same. Right? So you're just changing the variables. So for example, xy becomes uv. And you have an integrable function under the elementary region D. This should be D star. All right. So integrating under the set of variable xy is the same as integrating under the set of variable uv, except you have to multiply the Jacobian determinant. So going back to our first example of the area of the unit disk. So in this case, you have x squared plus y squared less than or equal to 1. Right? This is integrable function, right? Because you have a constant function. This is, of course, integrable. It's continuous, therefore it's integrable. Right? So we know that this represents the area of the unit disk, which is pi r squared. Right? So when you change from the Cartesian coordinates to polar coordinates, you have x equals to what? R cosine theta. Y equals to r sine theta. So let's compute the Jacobian determinants. This is partial x of partial u, partial x of partial, well, u is partial r, partial x of partial theta, partial y of partial r, and partial y of partial theta. So what is partial r of partial x of partial r? That is cosine theta, right? You should be familiar of finding partials. This point, partial x of partial theta is minus r sine theta. And partial r of partial y of partial r is sine theta. Partial y of partial theta is r cosine theta. Right, so the determinant of this 2 by 2 matrix is cosine theta times r cosine theta, which is r cosine square theta, minus r sine theta times sine theta, which is minus r sine square, which is plus r sine square. Right. Combine the factor r, they have common factor r, so r of cosine theta plus sine theta, which is 1. So the Jacobian for changing the variable from Cartesian to polar coordinate is r. So now integration becomes the iterated integral from the radius from 0 to 1 and the theta from 0 to 2 pi. The function goes from 1 to r because of the Jacobian d theta dr. For this part, right, it becomes 1 of 2 pi r. The antiderivative of r with regard to theta is just r theta, so it's 2 pi r dr. Right? The antiderivative of 2 pi r is pi r squared from 1 to 0. So right, 1 times 1 square is 1. 0 squared is 0. So 1 minus 0 is 1. Which is pi r squared. Right. So now these two integration would have the same results as we discussed. So let's say this is a disk of radius r0. So now everything will, you know, is good. So this is the case when you have a transformation in R2. Right? Let's move on to R3. Right? So in R3, the Jacobian determinant represents the change of volume instead of area, because you're now in R3, right, of this rectangular box, dx, delta x, delta y, and delta z. From this to the rectangular box, delta u, delta v, and delta w. Right. So when you change from xyz to uvw, of course the volume of the rectangular box will change, right? So when you're summing up all the Riemann sum, you have to account for this change of volume, and the Jacobian determinant would be the one to account for, the one you would need to account for the change of volume. So formally, the theorem of changing variable in R3 would be this. Right? This is the Jacobian determinant you need to apply when you change from one coordinates to the other coordinates, right, in other variables. So let's do some example. So for example, you have let's say a cylinder in R3, right, with the radius R0 and the height of h, let's say, right? Then you know that from the formula of volume of a cylinder, the volume should be equals to pi r0 h, right? So which means the integration of this triple interval should be equals to pi r0 square times h. Right? So let's use the polar coordinates. I mean cylindrical coordinates. Right? So for cylindrical coordinates, x equals to r cosine theta, y equals to r sine theta, and the z in the cylindrical coordinate is the same as the z in Cartesian coordinate. We didn't change anything, so the z is the same. Right? So in this case, we have z from 0 to h. Let's say the z-axis goes across the middle of the cylinder. So now you have the radius is from 0 to r0, theta is from 0 to 2 pi, and the z, the height, goes from 0 to h. So now we have to apply the Jacobian, right? So in this case, the Jacobian from Cartesian to cylindrical is the determinant of this 3x3 matrix. So dx of partial x of partial r, partial x of partial theta, and partial x of partial z. Do the same thing for y, so partial y of partial r, partial y of partial theta, and partial y of partial z. And finally, you have partial z of partial r, partial z of partial theta, and partial z of partial z. Since there is no z in the coordinate x nor y, so partial x of partial z should be 0. These are gone. This is 0. This is 0 as well. And for z, right, there's no r nor theta, so this one should be 0 as well. And partial z, of course, is 1. Right? And the partial x of partial r and partial x of partial theta would be the same for the one in the polar coordinates. You have cosine theta here minus r sine theta. And this is 0. Sine theta, r cosine theta, and of course 0 here as well. So 0, 0, 1. This is 0, this is 0, and this is 1. So the determinant for this 3x3 matrix, right? You can do this, you know, using different ways, right? The way I would do is to look at this row, right? 0 times the determinant of subdeterminant of this minus 0 of the subdeterminant of these 4 entries plus 1 times the subdeterminant of this. This is 0, this is 0, so we only have to look at 1 times the determinant of this 2x2, which is cosine theta times r cosine theta minus r sine theta times r sine theta. So this becomes the r cosine theta square plus r sine theta square. Of course, cosine square plus sine square is 1. So this is just 1. 1 times r, which is r. So now we know that the Jacobian determinant we have to multiply is r. R. This is the Jacobian. And this is r from 0 to r0, so this is dr. Theta 0 from 2 pi, this is d theta. Oops. And this is dz. Okay. The antiderivative of r is half r squared. So this becomes 1/2 of pi, r0 square. The antiderivative of this with regard to theta is half r0 square theta. So theta is from 0 to 2 pi, so multiply by 2 pi. And this, the antiderivative of this with regard to z is half r0 squared 2 pi times z. So when z is go from 0 to h, so times h. So this is the result of this integration. simplify this, you should get pi r0 square h. Right? And these two are the same as it should be. So this is how you do it in R3 cases. Right. So let's generalize things. Right. Let's look at the three type of coordinate system we are dealing with so far. So polar coordinates in R2. Right. So if x equals to r cosine theta, y equals to r sine theta, this is how we represent polar coordinates. The Jacobian determinant from Cartesian to polar coordinates is r. Right. And for our cylindrical coordinate in R3, the Jacobian determinant is also r, right, as we did before. The complicated one would be the spherical coordinates, and you can verify yourself. Right, the determinant is rho square sine phi. Right. So for example, if you want to calculate the volume of a unit ball or a ball of radius r0, from the volume formula, this should be 4 pi r0 cubic. So let's do the one in spherical coordinates. All right, so for spherical coordinates, you have theta goes from 0 to 2 pi. Rho, right, that is the radius of this ball, go from 0 to r0. And the phi angle is the polar angle, go from 0 to pi. Now you can set up the iterated integral in spherical coordinates from theta from 0 to 2 pi, rho from 0 to r0, and phi from 0 to pi. Right? Because the Jacobian is rho square sine phi, you have to apply the Jacobian here. So rho square sine phi. And this is d theta, d rho, and d phi. So the antiderivative with regard to theta is rho square sine phi times theta. Well, theta is from 0 to 2 pi. Right? So when you plug in 2 pi and 0, right, this becomes rho square sine phi times 2 pi. So this set of integration is gone. We have 2 more integration to go. D rho and d phi. Right. So the antiderivative of this function with regard to rho, right, is 1/3 of rho cube. Wait, did I make a mistake of the volume formula. Oh, the volume is 4 pi divided by 3. Right, so there is over 3 here that I over. I think 4 pi r squared is the area of the sphere. I think I messed up with the 2 formula. Anyway, now, right, the antiderivative of this is 1/3 of rho cube sine phi times 2 pi. When the rho goes from 0 to r0, you just plug in rho equals r0 here minus rho equal to 0 here. After you plug in, you should get instead of rho cube, you should get r0 cube. And finally, you have only the integration on phi to worry about. Right? The antiderivative of this is the antiderivative of sine phi times whatever this constant. Right? The antiderivative of sine phi is minus cosine phi times 1/3 of r0 cubed times 2 pi. The phi goes from 0 to pi, so plug in 0 and pi here. Cosine pi is -1, and cosine 0 is 1. So you have minus 1 minus minus 1, so which is 2. So you should get 2 times 1/3 of r0 cube times 2 pi, which is 4 pi r0 cube divided by 3. And as you can see, these two are the same. Right? You get the same amount of volume, just in 2 different set of variables. One is the set of variable in x, y, z, and now you have the set of variable in theta, rho, phi. Okay, but you get the same thing. Right? Apparently, the calculation is much easier in spherical coordinates than the one in Cartesian coordinate. All right, if you do the triple integral in x, y, z, right, the x is equals to square root of r0 square minus y square minus z square. When you represent the elementary region, right, go from the minus to the positive of the square root of r0 square minus y square minus z square, and y is the from minus r0 square minus z square to square root of r0 square minus z square, and z is from minus r square, r0 to r0. Apparently, you have a lot of square root to worry about, and that would make the calculation much more complicated. Right? And I would prefer, personally, I would prefer doing the integration on spherical coordinates. You just have to worry about the antiderivative of rho square and sine phi, and that's it. Much easier, I think. So that would be the end of the class. Any questions? All right. If you want, I can do the exercises or examples on the book. Give me a second. All right, so for example, let's look at example 6. Right. So now you have the triple integral where W is the unit ball. Right. So for unit ball, the easier way to make the change would be going from Cartesian to spherical coordinates. Right. So for spherical coordinates, the Jacobian determinant is rho square sine phi. Right. So x squared plus y squared plus z squared would be rho square. So this is integration of e to the rho square to the 3/2 power. You can put the 3/2 power to the rho square. It means e to the rho square to the rho square to the 3/2 power becomes e to the rho cube dv. So instead of dv, we can write it in spherical coordinates where rho, so d rho, d phi, and d theta. So in this case, we have to multiply the Jacobian. Don't forget about the Jacobian here. So let's write it this way. E to the rho cube rho square sine phi d rho d phi and d theta. Right. So this is the triple integral we should be dealing with. Right. These two should be the same. Right. So what is the antiderivative of e to the rho cube rho square sine phi with regard to rho? Right. So the antiderivative should be e to the rho cube sine rho divided by 3. Right, you can verify it yourself. Using chain rule, of course, you have a function of rho cube. Right. Right. So in this case, the rho, because it's the unit ball, the rho goes from 0 to 1. Right. So yes. All right, so this is the notation the book use the exp, the exponential, as the natural exponential. So that means the base is the e, natural constant. So this is another way of writing e to the x squared plus y squared plus z squared to the 3/2 power. Right. Okay, so let's go back. When you plug in rho equals to 0 and 1, this becomes e to the 1 power divided by e to the 0 power. So basically e minus 1. All right. And now you have to worry about the d phi and d theta. Right. So of course, the antiderivative of this with regard to phi is e minus 1 over 3 minus cosine theta in this case the phi, minus cosine phi. In this case, the phi is the polar angle goes from 0 to pi. Right. So cosine pi is minus 1. So minus 1 becomes 1. Right. Minus, when cosine 0 is 1. So minus 1, it becomes 2. Right. So the antiderivative of this, you plug in 0 and pi, this becomes 2. So now you have one more variable to worry about is the d theta, and the theta goes to from 0 to 2 pi. The antiderivative of this is whatever this is, because this is a constant with regard to theta. So times 2 times theta. Theta goes from 0 to 2 pi, so plug in theta is 2 pi here and theta is 0 here. You should get 2 pi. This is 2 pi. Right. Simplify everything, you should get 4 pi over 3 times e minus 1. And let's say you should get, 4 pi over 3 times e minus 1. Okay. 1 second. Any quick question? How does... All right, so remember rho is the radius, right? That's how we represent the radius. Okay. You can plug in, x equal to rho sine phi cosine theta, y equal to rho sine phi sine theta, and z equals to rho cosine phi. But the easier way to memorize is conceptually rho represent the radius. Okay. I guess that's it for the class, and you have the whole weekend to study. Again, the next exam on the next Tuesday, focus on the chapters 4.2, 4.4. Let's just put it here. So you have arc length. How to calculate arc length? The double integral on rectangle. That means you need to know how to evaluate iterated integrals, and double integral on elementary region. Right? How to represent elementary region in R2. Right? And finally, triple integrals. Right? So that means you need to know how to find elementary regions in R3. Right. Any questions? If there's no questions, the class is dismissed. So next Tuesday will have nothing to do with chapter 6. All right. This chapter will only appear in the final. Don't worry about this for next Tuesday.
Can I ask a question? Gone already?
The chapter for the topic on next Tuesday is here, right here, right here. Can you see that? Yes. Okay.
Can I ask a question? Can I ask a question?
Oh, I'm sorry. I was away for a second. Peter, what was that? What was that picture about?
Yeah, that picture was a function from the homework, which failed. I think it was Fubini's theorem we were supposed to work on, and in this particular function, the change of order of integration didn't
Yep.
work. Didn't work.
Yep.
And
Because it's not integrable. Yes.
But
you can see that you have a breakpoint in the middle.
yeah, you can see you have a breakpoint in the middle because the function is not defined at 0, 0.
Exactly. So when you have the integration, it shouldn't work. So when
Just
you have
for
the
that
Riemann
reason.
sum, yeah. So when you do the Riemann sum, it won't converge.
Right. So that's the
why
only reason is because of the lack of continuity.
The technical reason is that it's not integrable. Right. So why it's not integrable? Visually, you can see there is a at the pole here is hollow.
There's a hole in it.
Yeah, there was a hole in it. Exactly.
But the Fubini's theorem allows a finite number of discontinuities, right?
No. What should I say? In this case, it's not right because there's a hole here.
Yeah, I believe that.
Right.
A hole is different than a discontinuity.
No. That in order for Fubini theorem to apply, it has to be integrable on this. Right. The function is not integrable.
But just because a point is missing, right? Because it's not defined at 0, 0.
Because it jumps to infinity here. So everything here is not bounded. Right. So the whole integration would jump when you do the Riemann sum, the whole thing would shoot to infinity.
So it's not bounded.
Yeah, exactly.
But the problem is when I looked at that function, are you familiar with the function that I'm talking about?
Okay.
I don't remember what the function was anymore. I'm sorry about that. But when I looked at the function.
Yeah, I know it has a fraction. That's why there is a jumping here. I can see the picture. Let me share the picture here.
Yeah, so right. it goes off to infinity, but when you look at the function, I think it was x squared minus y squared over x squared plus y squared to the squared.
Yeah, so it's not necessarily everything goes up. There is some portion of it jumping down.
Right, but I didn't see why the jump occurred. The jump has to occur because of some going to infinity.
It's not the jump. It's just you can see in this dark region, this part is going up, but in this region is actually going down. So you have two set of things.
So you have
and there is breakpoint here. So it's kind of like a saddle. It's kind of hard to imagine, but try to imagine it.
Yeah, I see what you're saying. Okay, I'm going to look at the function again because the function really made my head spin. I don't know why.
Right. So when you do the Riemann sum, right, one way to partition it is to partition everything positive together. In that way, you have a positive integral. But if you partition it in a different way, you would get another number for integral.
Okay.
And this is why Fubini's theorem doesn't work. Wait for 1 minute. I have something to work. Yeah, I'm back. Yes.
So I know this function is like not integrable, and like the Fubini theorem doesn't apply.
Yeah.
Is there a quicker way to recognize? I see that it's a quadratic kind of like related. Is there a quicker way to realize that the Fubini theorem won't work? Like just by the
um, in reality, there's no shortcuts. All right. So that's why for this type of question in the exam, you won't have to recognize whether or not it is not integrable. However, I would make a not integrable function and let you verify that the Fubini theorem doesn't work by doing iterated integrals in two different orders. So you just, like the homework question, do it in two different orders and see it doesn't work.
okay.
Makes sense? Yeah. In order to verify a function is not integrable, you have to find the limit of the Riemann sum, and it's just so technical and almost impossible for every function. Make sense?
But when you take the limit of that function in any order, you never get it. It never seems to go to infinity.
Right, because in dx and dy, when you reduce it to iterated integral, you just fix the direction, right? So you just fix the partition in x and y. Of course, you can do it in, for example, y equals to x and y equals to minus, this way, right? So in that way, the whole thing would be everything goes to infinity and the other thing goes to minus infinity, and they will cancel out.
Okay.
Right. So again, because it's not integrable, the way of changing the order of integration or the way of doing the partition matters, because you would not get a convergence series anyway. Right. I will be right back. All right. Very good. Very good.
Thank you. Have a good weekend.
You too. Thank you for participating.